All right, we're finally up to entropy. Last topic before the next test. So, and being straight with you, I don't do a ton with entropy. You'll see when you get to the worked problems. So let's get through this as quickly as possible. There's also lots of amazing videos online. I'll try to put a couple links in there from ones I've seen that are maybe a little bit more in depth, that have cooler visuals than what I'm going to do. That said, let's plow through this as fast as possible, give you the briefest introduction possible. Entropy, capital S. It's a measure of disorder. A system with lots of disorder, lots of randomness, has a large value of S. It's a measure of the quality of an energy source. And by this, I mean, if you have low entropy, you have high quality. All right, so think about it like this. If the energy is very ordered, it's very easy to make that energy do work because it tends to become randomized, right? So said another way, if you have high entropy, not much energy available to do work. So these two are kind of like flip-flopped of each other. I don't know if that's contrapositive or converse. I don't care. Whatever. So the less disorder you have, usually the more useful the energy is in a system. A very kind of technical definition here would be a measure of the number of microstates and we use W for that, right? So, and you could use K Boltzmann log of W. So this already gives you an idea of the units on entropy, doesn't it? Log has no units. The argument, number of microstates, a number has no units. So the units are K Boltzmann, which is what? 1.381 times 10 to the minus 23 joules per Kelvin. All right, and that's on the back somewhere. I don't know, where is that? I thought I put that on there. Yeah, it's in there somewhere. All right. It's a measure. It's also a measure of energy dispersion, right? When the energy is really spread out and dispersed, it's low quality. It would be high entropy. So, all right. Change in entropy. That usually ends up being something people do in thermochemistry all the time. So if you're in chemistry, you might wake up now. All right. So change in entropy is given by ds equals dq over temperature. So in a physics class, we might make you integrate this. So a classic thing I could make you do is, well, a lot of times you might say the change in heat is NCV times dt. So if you add a tiny differential amount of heat, maybe in a constant volume process, there'll be a tiny change in temperature. Notice you can drop that in and do the integral, and that's how you might be tested on this. That's one way, right? You could quickly do that. Now, the change in entropy is always positive for real processes if we account for the entire system. You'll often hear this, entropy always goes up, entropy always goes up. Yes, but it is possible to have entropy of something go down as long as another part of the system goes up by a larger amount. And that's what I'm trying to indicate here. For example, let's say you have maybe we're freezing some ice, right? So the water changes from, water changing into ice would be a negative entropy process. Well, something over here would have to change by a larger amount, right? So you're, right, to cool off the ice, you'd have to warm up some liquid nitrogen and change it from a liquid to a gas, perhaps. And so that would work. You could freeze the water, make this term have a negative change in entropy, but you'd have a much larger positive change in entropy for, say, the liquid nitrogen. All right, and a quick couple of things over here. By the way, I'm looking on pages 104 and 105. Volume 3, if you want the page numbers. The second law of thermodynamics. In any real-life process, delta S of the system is greater than 0. So that's the second law of thermodynamics. That just has to be true. There's another version of this. All real-world engines are going to waste heat. You can't just have all the heat come in and get all useful work out. The work net is going to have to be less than Q input. There's always going to be some waste heat. Another way to say this is the Clausius statement. Heat does not spontaneously flow from cold to hot. You're not going to have thermal energy just randomly go up unless you put in some work, or unless you have a heat pump. Now, a corollary or a third law that you'll sometimes see is that it's impossible to reach 0 Kelvin in a finite number of steps, which corresponds to the maximum theoretical efficiency of an engine is going to be 1 minus T cold over T hot. And that's, what is that, 2 adiabats, 2 isotherms. If you want to derive that result, it's on, let's see, page 98. Problem number 20.5. I dig into the Carnot engine, Sadie Carnot. And again, I'm just trying to get this done as quickly as possible. I'm going to link some other videos. I'm just giving you some terms. We've got to do a couple of problems. We'll do that in the workbook. All right, let's call that good.